Hello everyone, my name is Ganesh Vishnu Gadge and I am here to give a presentation on electromagnetic thruster under the guidance of the Professor Yuvraj sir. Now let's see what is the electromagnetic thruster. Electromagnetic thruster accelerates ionized the propellant through either self-induced or applied magnetic field. The force expressed by the Lorentz law, which is given as the FL is equal to I into L into B, where I is the current induced, L is the length of the channel, and B is the magnetic field. The high electric currents need to generate thrust requires high power levels, turns up to kilowatt up to megawatt, or pulse regeneration with the heavy capacitors. Electromagnetic thruster can be classified into three types: magnetoplasma dynamic thruster, that is MPD thruster; pulsed plasma thruster, that is PPT thruster; and the variable ISP plasma rocket, that is VASIMR. Now let's see what is the magnetoplasma dynamic, that is MPD thruster. In MPD, magnetoplasmatic MPD thruster or a low nut force accelerator (LFA), a high current discharge, a kiloampere less than 100 volts, is applied between two coaxial electrodes. The discharge ionizes the propellant flowing through the electronic compression. A variety of non-oxidizing propellant can be used, such as hydrogen, argon, and even alkali metals like lithium. The current generates as a self-induced radial magnetic field that interacts with the current, as shown in the animation, resulting the Lorentz force acceleration, that is thrust scale to the I square, that is the ampere voltage square. The coaxial component generates the thrust and the radial component increase the pressure towards the central line. The propellant flow and the thermal gas expansion, temperature higher than the 2500 degrees Celsius, also contribute to the thrust, but are usually at least one order of a magnitude below the magnetic acceleration. This principle is called as self-filled MPD thruster. An additional external magnetic field can be added, permanent magnetic coils or magnet or coils around the anode to increase the performance, which is also known as the applied magnetic field MPD thruster. MPD thruster can generate a high thrust up to 200 Newton and can transist to very high power levels at a specific impulse of 8,000 seconds. The higher the power, the better the efficiency, which is typically around 35% to the and can be increased up to 75%. The performance characteristics make MPD thruster very attractive for a manned mission. Obviously, these are the high power requirements can only meet in a combination with the nuclear power plants. Also, ground testing is very difficult. One of the few test centers with vacuum facilities are as available as for a power continuation operation of MPD thruster in the Institute of Space System at the University of Stuttgart in Germany. The many other research institutes use an MPD thruster in a pulsed operation with a large capacitor bank. The cathode erosion is one of the major life limitation factor. However, being developed since 1960s, MPD thruster have already demonstrated lifetimes in excess of the 1,000 hours. A pulsed MPD thruster was successfully flown by a Japanese Institute of Space and Astronautical Science (ISAS) in 1997. The research on this thruster is currently being carried out by NASA, JPL, Princeton universities, and several Russian institutes such as the Moscow Aviation Institute and European and Japanese laboratory. Now coming on to the pulsed plasma thruster. A pulsed plasma thruster is a very simple electronic propulsion thruster. A solid propellant bar, usually Teflon, fills the gap between the two electrodes connected to a capacitor bank. The spark triggers an electrical discharge across the surface of the propellant. The heat transfer from the discharge absolute parts of the propellant and ionizes it. The ionized propellant is then accelerated by the electronic field as similar to the MPD thruster. A simple spring advances the bar axially for the propellant resupply, as shown in the animation. One shot proved a thrust of 10 to 100 of the micronewton. The thruster usually operates at a frequency of 1 to 3 Hz. A PPT thruster has several advantages like zero warm-up time and zero standby power. No propellant tanks at feed lines, and most probably, notably, it is a very cheap due to a simple design. The main disadvantage is very small efficiency between 5 to 15%. A PPT thruster was successfully found on a Soviet Zonad 2 spacecraft towards Mars as early as in 1964. several applications followed in the United States. Presently, PPD thrusters are under evaluation for a fine altitude and the position control for formation flying satellite on account of their small impulsive bit capability. Now coming on to the variable ISP plasma rocket, that is VASIMR. A plasma rocket uses a magnetic field to combine a plasma and electromagnetic energy to heat it. In a VASMR concept, hydrogen is ionized and injected into the main chamber by a magnetoplasmadynamic, that is MPD device. The magnetic field isolates the plasma and the chamber walls so that the temperature can exceed the material melting limit and therefore reach very high specific impulse. In the main chamber, electron and ion cyclotron heating is used by applying the resonant radio frequency RF field to heat the plasma, which is then expelled through the magnetic nozzle. Hydrogen propellant can be injected into the plasma exhaust for a cooling purpose. The magnetic nozzle can control the thrust by varying the nozzle intersection. On the other hand, the specific impulse can be varied by changing the RF heating power from 3000 to 13,000 seconds. This enables to change the thrust and the specific impulse independently of each other and enables the performance to be tolerated at a specific mission. Work on the VSR concept was conducted at MIT Plasma Fusion Center in early 1980s, and it is presently going on to the Advanced Space Propulsion Laboratory, NASA's Jones Space Center. A small-scale VSR prototype is scheduled to be tested on board International Space Station to verify the performance parameter. The characterization of electromagnetic thruster can be done as follows: for a two thrust mode, steady state and pulsed. And the magnetic field source can be for a steady state it is the external coil or a permanent magnet, and for a pulsed it is a self-induced. The electric current source for a steady state is a direct current supply, and for a pulsed it is a capacitor bank and a fast switch. The working fluid for a steady state is pure gas mixture, seed gas or a vaporized liquid, and that equals to for it is a pure gas or a stored gas solid. Geometry of path of the working fluid for a steady state is axisymmetric, coaxial, rectangular, cylindrical, constant or variable cross section, and but for a pulsed it is axisymmetric, ablating plug and other. For the special feature of the steady state are using a Hall current or the Fed current, and while the pulse mode thrust mode increase uses a simple requirement for a propellant storage. That's it for this topic. Thank you.